right? You want to share your screen, Christine?
Finding, wait a second. Can you see the screen?
Yeah, that's good.
Yeah, so I reported with multiple temperatures with blue is the precursor as synthesized,
Mm-hmm.
and 550, 700, 800, 1000, 1100. And as you can see from the
Mm-hmm.
uh, XRD analysis, there's a lot of tellurium and tin bases and some of tin and telluride, tin oxide.
Mm-hmm.
Yeah, and I'm not sure which phases it should form on its, and I want to get feedback from Haiwan as well.
Okay, so Christine, I think it's quite complicated. Previously, when I was pursuing zinc vanadium 3 oxide, I think Kida and Chengguang still recall, I almost spent a week to decouple like about 50 XRD patterns manually. So I will definitely need to spend a half day with you together to learn what's going on here. In facts workstation, and we try to manually crack this files first. But another method is, if possible, I'm not sure if Pepe is able to help, we can pass these patterns to Pepe.
Yeah, just send it. Don't think. Whoever,
Yeah, that's going to be easy and quick.
yeah, just send it over to Pepe and say, hey, we made some new materials. We can explain it later. Are you able to do right for refinement and see what the phase is?
Yes.
But again, this, yeah, I mean, and tell him that there's theoretical XRD pattern available. And I don't know how much time he has because I think he's going to be on some personal leave for the next week or two. Okay.
Oh,
So but you can ask him. And I think they
yeah.
have automated rifle refinement code.
Yes.
We can just take some time to run it and send it back to you guys. But I mean, if you look at the peaks, to me, there's a question I asked was, if you look at it just looks the same, right? 550, 800. I mean, there's nothing to resolve here. Nothing is reacted. I think the tin and the tellurium just forms a little bit of oxide and then nothing is reacted. Like, what does can you get, like, I think Chengguang or someone can help you do the EDS? I mean, Haiwan, can you help do the EDS? And then I think it's just unreacted tellurium and tin. This is what I see. Isn't it true? I mean, what do you guys think?
So is it supposed to form like tin telluride or?
Yes, I checked very briefly. Like, tin telluride should start to form at 700 degrees Celsius.
I
Or,
mean, I would say I would need to see the ball mill XRD pattern first.
hmm. No, I mean,
But yeah,
all the peaks here are explained. Like, if you zoom in here, right, Christine, at the bottom left, isn't it already matching? It's saying that 96% is tellurium, 10% is tin.
This is the ball mill one.
This is the ball mill one, right?
oh, this is the ball mill. Okay.
Yeah, but then if you go up here, you see the peak locations basically stay the same. If anything, they're sharper. Okay, there's a
Yeah.
little bit of a shoulder that's forming, maybe, yeah, maybe this, right? But this is the same. This is the same, this is the same. This is the same,
Yeah,
same.
some secondary phase is forming. Yeah, below like
Little bit there's a broadening, or maybe that's the oxide, but most of the peaks don't change. I mean,
like
it's the same here, right?
Yeah, I think it's just unreacted. So this is the ball mill, if this is the ball mill then.
Exactly. I feel like it's just not reacted.
So for potassium, you still use potassium nitrate or potassium carbide or carbonate
Potassium
or
potassium nitrate, but I think it's if we have a potassium carbonate precursor,
carbonate.
I think it's we can try with that one,
I mean,
because the problem with the potassium nitrate, it's it it's very sticky and is very hard to
Explosive too.
remove.
do you
Explosive.
That's good. Do you have the video from the DJS of this one, Christine?
No.
Okay. So just like for new compounds, I think it's a good idea to take a video. Just take your phone and when the reaction is happening. Can you walk us through it? What does it look like compared to the regular, you've done like germanium chloride, AST and iron, you've done like all the nice synthesis, right? Compared to that, what does the DJS look like?
Okay, I will for let me see show photo.
Yeah, man, we may not have the potassium carbonate precursor already, right? We might have to buy it.
When you're using nitrates or carbonates, it's very hard to get the metallic, like raw material phase. You cannot avoid the oxides. Typically, people use if you use nitrates or carbonates, copistrate, then you will get the metallic powder. Those powders you can use as a DGS for the DGS, because if you use nitrates, it's not easy to remove oxide. I don't know. I will see.
Yeah, I fully agree with Mahesh. Previously, when I was doing zinc vanadium 3 oxide, there were upon the time I used direct sodium metal in the ball mill,
And
but of course, a bit of
yeah,
caution is
cannot use.
required.
Yeah, yeah. And
Yeah,
I mean,
I think I learned from you, right, Mahesh?
yeah, yeah, yeah. You can use still nitrates, but you need to do powder preparation first using like soldier or co-precipitation method. Bring out all the raw material by co-precipitation. Like co-precipitation is nothing but salts plus minus
Yeah,
you add. Then bring that powder you can use as a DZS
yeah,
because it's,
I think soldier is.
yeah, soldier still
That's like
covers. Yeah,
developing a
still.
new process, man.
I mean, for initial raw material, not easy to get from the oxide. If you are trying DJs directly burn and how it looks, I'm also curious to see.
So we've done potassium nitrate
Yes.
for the catalyst materials and it works, right?
Is
For
it,
catalyst material, yeah, we will need like dope. So we'll need
Only
less
5%, 5 to 7%.
5%. This
very
is
hard to gather? Typically, I'm curious also.
But that material, the potassium goes everywhere. We've shown
Mm,
that it goes everywhere, right?
nice.
You have the data, Christine? Maybe you can show them.
Yeah, better to use carbonate.
Yeah.
for the
Nitrate generally
ESO
used for
or
soldier stuff.
Yeah,
Mm.
like
Just
salt.
show them you have an EDS of the catalyst samples, Christine, that you made. Anything?
yes.
Yeah, just it'll be good for the group to see what you and Delvin have made so that they know that this is possible. It gets a bit crazy with a lot of potassium too. I think it starts oxidizing like crazy and it burned the paper, right, Christine? Was that the
Yeah.
potassium nitrate? Yeah, or the sodium? I don't remember now.
Yeah, yeah, when you are using, we generally use sodium chloride and co-precipitate it, like soldier or whatever co-precipitate it. Then you can get back the sodium because the chlorine can mix with water or something, sodium ion and chlorine ion. Then chlorine ion is get solvent dissolved in water. uh, then the sodium will be co-precipitate with the whatever the element like Na something. Then that powder you will take
Mhm.
out typically. Here, same. Nitrates also can easily mix in the solvents. Then whatever the metallic ions, those are ions. If you want to bond with another anion, you can do. You can
Mhm.
do. Yeah. And just show me the potassium nitrate which you used.
This is the EDX pattern.
This is with sodium, not potassium.
Yeah. I mean
Oh yeah,
sodium.
this is with sodium
Similar,
and
sodium nitrate.
Yeah,
wait,
can.
potassium. Wait, let me potassium.
I mean it is mixing well in the matrix. That's good.
It is, yeah, it's going everywhere. But as Christine said, it's not very high percentage. So here, I think the molar ratio is much higher, right?
Mm. Did you find oxide peak particularly? There's some at 550 some other letter. What is this? Potassium.
Potassium.
Nice, actually.
Yeah, pretty good. I mean, I wouldn't say fully homogeneous, but it's there. It goes everywhere.
Yeah, it's not like
Yeah.
cloudlet.
And the catalyst performance shows that it goes everywhere because without that potassium promoter,
Mhm.
catalyst does not work, which means that you definitely have potassium going everywhere.
Nice.
All right. I think that's the point.
Yeah, go back to the XRD which we are presenting now.
You
Sorry.
can delete this. It's okay. It's just to show them.
Do you find the shoulder which is like 28 2 theta is about 28 something? Um, yeah, there's some secondary phase, right? Sorry, which you are putting.
28. Wait a
No,
second.
2 theta in XRD plot.
The 28 degrees,
Yeah, sorry.
I don't think there's anything.
Yeah, like bar milling is fine. What is the secondary phase like? Oxide more or do you
This
find
one?
any
This one I couldn't index it.
maybe what did you try? Like indexing means only did you try oxides? No.
Like I tried tin oxide and then tellurium oxide
Okay.
doesn't work.
Okay.
And if you look at the theoretical, there's nothing there. If you go up
Yeah.
to my project at 20, this is below like 24 degrees something, right?
And it also doesn't really match with the theoretical one. And
So Hyman, when you did it for zinc vanadium oxide, was the theoretical XRD good to solve the structure or it was not?
So the final spinel structure, yes, 100%. But the beginning predicted structures in materials project, not at all.
Hmm.
So it's basically, we still use the serious manual process to figure out what's going on.
So who was on the call yesterday? Christine, were the people from Japan there?
sorry, which one?
The meeting yesterday when you presented, who was there on the meeting? Was
June and um
Masato?
Masato was there.
Hmm.
Uh
Okay.
Raymond, Jayu, Tomiya, Martin, Suya,
Okay.
Jayanta.
Jayanta, what do you think? Mhm. Mhm. Okay, let's. Mhm. Can you show the paper?
Genta, is it within one of the papers previously I put it in the folder or not?
Guys, the first few compounds are definitely going to be hard, okay? Because we need to figure out the process, right? What do we do? Do we need to have a synthesis predictor from literature? It is normal. Okay, every time we try to do something new, it's going to be hard. Hopefully, we come converge in a process that we trust. And what tool to use? This is just how it's going to be. He put the paper in. Okay, let me open it. I think this is the same one you put in, Ivan, to answer your question. Let me share. Where is it? This is all in German, no?
Oh, crazy. That's definitely the same one. I got very bad memories on this paper.
me ask ChatGPT to translate it.
Yes. But I'm pretty confident that they did two things. The first is they used pure potassium. The second is they sealed it in a core sample.
Okay.
So that's the two key things they are doing.
Okay. Now the question becomes, how do you
I mean, I feel like there is one thing we are able to do. So we just use potassium in the glove box, and then we let the DJS process all in the glove box, wait for the reaction to finish, and then we take out the sample from glove box.
okay, wait a minute. Translate to English and extract the synthesis.
I mean, for me, I used it, I ball milled it. So long as doing ball mill, it's argon sealed. When I open it back, it's also in a glove box. I feel it's safe.
Okay, here's the translation. Tin and tellurium were weighed in stoichiometric proportions into a corundum crucible inside a quartz ampule, pre-dried at 120. Then the ampule is flushed with water and oxygen-free argon. And then because argon is heavier than air, so you don't need to go glove box, okay? So when you flush something with argon, it displaces the oxygen, right? So it'll remove any water vapor and oxygen. This works quite well. In fact, in IMRI, we did this once, and this is even for very sensitive polymer synthesis that is very hygroscopic, like water sensitive, it still worked. So this idea of just taking argon and putting it in your plexiglass for your DJS should work. So because potassium unavoidably reacts with the corundum and the quartz walls, 10% excess potassium was added. Okay, I mean, this is going to be a problem for you too, because you're using quartz as well, right? We don't have a corundum. Corundum is alumina. Okay.
What we had are quasar corundums, so
Sorry, what?
everything will react.
What's that? Sorry?
I mean, I think the DJS tubes we have is either quartz or aluminum oxide.
Yeah. So what I'm saying is you just need to put excess potassium, right? This is
Yeah.
the other thing. Maybe there's no potassium there because maybe the potassium is reacting with the quartz. And so it's not
Then,
reacting with the tin or tellurium.
yeah, because these elements easily people use to change the color of glass to
Mm,
easily react with glass or quartz.
true. Sodium and potassium go easily react with glass. You're right.
Um,
Or any oxide,
did
aluminum.
the quartz tube change the color?
Use
Some,
the
okay.
use the platinum foil.
Yeah.
I'm experienced, right? So I can tell. Use platinum foil. I'm
Christine,
using.
did the glass change color? Christine, did the glass change color after the reaction?
Yes, and it sticks on the quartz tube and
Yeah, they will react and go in the quartz glass everywhere.
Reacting for sure.
Yes.
Because potassium reacts. Okay, so let's read this.
Yes.
The ampule was evacuated, sealed, and then placed in a tube furnace, which is alumina. Then heated under argon to 750, held for 1 hour, and switched off. It produces metallic gray plate-like crystals. Stable to air and moisture. I think you can try it. Okay, I'm going to send you this, okay? So what I mean is this is sort of the protocol that you guys have to start developing and using. Go to ChatGPT and use that to come up with synthesis recipes. So you know what I do next? I say something like this. Okay. Can you guys see my screen?
yep.
Okay, so I'm going to do this. And I think Jayanta has access to my ChatGPT. Christine, so just work with him. So does Delvin. Okay, just get the password and do it. So let's just take the latest draft. Okay, we're setting the nation synthesis. Let's take the manuscript, which should have all the details. Based on this DJS synthesis, how would you do the reaction? Okay. What I mean is this is just going to be a pipeline. So instead of going through and trying to solve it, just try to come up with synthesis recipes also through L. We can always automate this. I mean, I think Danny is not here, but we should be able to do it. Okay, let's see what it says. And so I use ChatGPT 5, okay? That takes the best of all models. Okay, so this is correct, right? See, current through a spring compressed powder bed packed inside a shortcut. So it's exactly correct. Right? So is give it to okay. Well, now it's mistaken because it's saying silver antimony. Let's see if it fixes itself. I push GPT a lot. Okay, blah blah blah. It's not giving you a good answer. Hold on. Wait, okay. It's being pushed quite a lot.
I think you are running out of memory. I mean, you still recall there was a student using Mac in your like machine learning class, and he was trying to use ChatGPT, and his ChatGPT was like 1 second per word speed. It was because of memory.
The precursors are KNO3, tin and tellurium metal, right?
When I asked ChatGPT about KNO3, they don't recommend KNO,
They don't recommend what?
potassium nitrate.
They don't recommend it. Yeah, I mean, I sent you that sheet, right? So, yeah, see again, we can take a look at this. It gives you considering K2 options. Ibrahim Telluride or K2CO3 could be better.
K to TE, can you find that, Prakasha?
I don't think that exists.
The potassium telluride, I found it. There's no precursor. We have to make it
We have to
from
make.
the potassium metal.
I think this is what you're getting. The K2O is too small because the potassium reacts with the glass. You're
Yeah.
just getting some TO2 and most of it is unreacted. Guaranteeing face trash and safety.
Guaranteed face trash.
Uh, it's coming. This is basically the same recipe as that. So it's two-step, which is you make the powder and then densify. Because once you make the material, it's stable.
Yeah.
Well, then you have to follow the recipe in the paper and do it in a glove box.
Try
This
to
is
check.
one shot.
I
So,
think one shot is also possible, right?
yeah. So you got to make this potassium telluride. Okay, even the carbonate is not recommended. Okay, I think it's clear, right?
Yeah, we gotta use K. Potassium.
How dangerous is potassium?
I mean, definitely not as dangerous as sodium, I feel.
Okay.
Definitely
Oh,
not
slightly
dangerous as the
more
lithium.
dangerous, right? Slightly more dangerous, sorry.
Yeah. Lithium is more dangerous. Potassium is still okay.
Potassium is still
But
okay.
still, I mean, still they can break the glass jars. They can break the sinks. Yeah, it's not blast. It's like it still can break the glasswares.
Christine,
So,
I will have a chat in lab with you because I worked with sodium for quite a bit of time.
so I think that this is it's in a way it's aligned with what you guys are saying, right? We should make the potassium telluride. So Jayanta,
Yeah.
Ivan, you guys, Mahesh, you guys see, right? And let's come up with a step. I think
Um, the easiest way, I need to check the literature. The easiest way is co-precipitation. It's very safe. Use salts and just co-precipitation method. I forgot the explanation. Sorry, I used long time back. But
Yep.
you can easily prepare the using co-precipitation. Still, soldier is more little dangerous. I mean, you need to be there and you need
the
Yes.
to
problem is
combust.
Sol gel also produces oxides.
Yeah, we don't want a soldier. I would like to suggest the co-precipitation method. Any literature, I will check.
But co-precipitation, how do you do that with pure metal? I think that's
Yeah,
hard.
yeah, yeah. Yeah. No, co-precipitation is easy. Like salts, potassium nitrate or something, and then your tellurium nitrate or another compatible salt mixed together in the some solvent. Then the potassium ion and tellurium anion they automatically precipitate.
Okay.
Yeah, I
Um,
think it makes
And
sense.
then-
We just need a potassium salt with a tellurium salt of certain type, and then they will
I need
co-precipitate to a potassium telluride, right?
Yeah, yeah. I know, but I need to check few. I prepare some co-precipitation salts before.
So, Christine, Soumya has access to a co-precipitation tool. He,
Okay.
okay,
Yeah,
so
just only small heater, 50 degrees centigrade, some stirrer, magnetic stirrer, and then some particular solvents. Yeah,
we can just ask him to do the co-precipitation. So, what maybe is the way to do it is we do two in parallel. One is
yeah,
if you find a safe way to make potassium telluride directly,
yeah,
okay, then we do it in the glove box. If there's a safe way to do it, talk to Jayanta and Havan, plan something because Delvin's not around, and we try it in our glove box because we have a glove box.
yeah. Try less quantity first.
And then all you need to do is make potassium telluride, try less quantity, right? If
Uh,
you're able to index this phase, then you know that you've made the precursor. Then DGS should be straightforward,
Yeah,
right?
you don't want to try potassium carbonate here?
No, it says the oxide is bad.
same. Potassium
Oh,
carbonate also kind of more or less same.
Yeah, so I think we'll waste time. Yeah, so see, you weigh potassium and tellurium. I mean, you can even try and borrow the platinum foil.
tantalum foil. It's not telling. Say tantalum foil.
Just
Yeah,
tantalum. You have platinum, right? You can
Yes, correct. That's why I'm saying
okay.
platinum.
Add a few tellurium comes on top. But I think we need to do like a slow temperature synthesis.
Maybe you want to coat your carbon with some metal like platinum coating.
Mm, this is not easy.
Yeah,
I mean, just doing this is a whole process, huh?
yeah.
How hard is this, Jayanta? Yeah.
yeah.
K2D is easy, right? Yeah. Making K2D is hard.
You guys already have potassium.
Mm.
Yeah, we already have potential salts, right? Co-precipitation is faster, is easy. Just need to find a right solvent, like or aqueous or anhydrous, some kind of solvent region we need to find. Um, check gather co-precipitation K2TE using yeah yeah
Plus TiO2, maybe?
no TE nitrates TE not O2 oxides is not easy to break. Nitrates or chlorides or TE salts.
Let's see what it says.
So in Wikipedia, it already says how to make potassium telluride. You need to react
Okay.
tellurium with KCm, potassium cyanate, in production of that. But I think if this reaction is well recorded, we should try to find the supplier.
Okay,
Yeah.
potassium telluride. But the potassium
Yeah.
telluride itself is, if you look at it, it says that it's somewhere it says it's air moisture reactive.
Mm-hmm.
Oh,
It'll oxidize.
Yeah.
oh no.
See.
Like the same as potassium, right? So however they
Means
set.
you cannot buy, you need to prepare, and at the same time, you need to prepare the compound.
So which means that it cannot be prepared by just normal copper precipitation in aqueous solution for sure.
No. You can precipitate, you can find, you can prepare. Then immediately you need to use to that powder to make a compound. So
No,
you
no, no,
cannot.
no. I mean, if it is moisture sensitive, how do you make
So
it in an
that's the
aqueous
reason I told
solution?
whether it is anhydrous solvent required or hydrous solvent required.
Ah, okay.
I told, yeah.
I got what you mean.
Yeah.
So now aqueous then.
The-
Yeah, potassium telluride is here.
Hmm.
It's a
Oh yeah,
monohydrate.
it is also still salt. So now is potassium. This one is there, right?
No,
You need to
no.
do
This
tin.
is okay.
This is K2TeH dot H2O, right? This is fine.
Yeah,
This raw material you can take and use tin salts also to get the powder.
No, I think it's a different material. So we want is potassium telluride. This is potassium
Yeah, salt,
telluride.
salt.
It's a salt.
Yeah.
salt.
It's
So,
not like a semi-metal or something.
no. This still this you can use. This is the precursor for making the compound.
For making which
Time,
K2TE.
yeah. K2 SNTE something, whatever the compound you decide.
Are you sure this is
Yeah.
oxidized?
This is no dot H2O. This is kind of
No, 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 no. It has an additional O inside.
yeah. These are the salts, kind of, right?
I mean, no, this is for sure not K2TE.
No, this is not
The
K2TE. K2O3TE dot H2O. So it will be dissolved. When you dissolve, there will be K2TE precursor there.
no,
And
no,
then,
no.
No,
Let me
oxygen.
send you
Why
the
there is oxygen?
sigma Aldrich link.
There is oxygen there
Let me
also.
Yeah, there is an additional oxygen there.
Oxygen
Let me send you
K2O3.
the yeah.
K2O3.
Yeah,
okay.
what you the potassium is already oxidized.
Yeah,
Yeah, it's
K2O3D.
already oxidized. It
Mhm.
doesn't work.
Mhm.
Already have.
Yeah, I sent you the sigma Aldrich link. You can see the tellurium is bonded to oxygen.
This is what you guys
Uh,
are using, right?
that is not easy to break.
Not easy to break.
It's not easy to break.
You will.
Any results from co-prestation? Sorry. Yeah.
Don't.
Yeah, don't aqueous. Don't aqueous.
Don't.
Yeah, you need to take anhydrous. No aqueous solution.
Okay, wait.
There'll be like anhydrous ethanol, anhydrous kind of some definitely there's some literature. Definitely we'll check. I need to check, man. Yeah, you cannot use in aqueous solution because sodium, potassium, they are react with water.
Just curious, why you don't want to try potassium chloride?
See, anhydrous. Yeah, THF.
Yes, metathesis.
Yeah,
Yeah, you need this.
yeah,
Yeah,
yeah.
oh, you have
Oh man, like given everything.
Actually, you can remove oxygen from tellurium. I remember Sayed used to remove using he used to make tellurium nanomer from tellurium oxide.
How?
He has some reaction putting
Yeah,
hydrogen actually hydrogen. It's
yeah.
a reducing agent.
Hydrogen.
Yeah, it's
Yeah,
a reducing agent. You put tellurium oxide, it will remove to tellurium.
yeah. But now question is potassium. Yeah, yeah. Okay, good.
There should be some reducing agent which remove the to break this bond.
Is it liquid hydrazine, right?
No, it's a powder, I think, or liquid. I need to check. We have that chemical.
Hydrogen. Yeah.
I will send you the link to this chat.
Hmm.
It's kind of crazy. But you see, even synthesis recipes,
Yeah, not straightforward.
it's
Uh,
giving
uh,
information. I don't know
we
how
can't.
why it's going a bit crazy. I can't help.
Have limited knowledge.
Knowledge. Okay, so I will send this chat to you guys. Okay, let's not be overwhelmed a little bit. But turns out, and you should document this somewhere, like starting with any potassium precursor without oxidizing and then reacting with tin and tellurium is hard.
Maybe you want to check with Kanishka. He was saying he used potassium recently for some materials.
Hmm.
How they use, I don't know. They have used potassium also for dope. I think for doping maybe.
Hey, can you download this Chinese paper? I send the chat box. The K2T preparation. Anyone?
I downloaded. Let me also try.
Uh,
Hydrazine, highly toxic. They say. Let's not do that. First of all, let me go through the hydrazine stuff.
It's not that toxic because Sayed was frequent user of hydrazine.
Hmm.
This is a tellurium oxide and potassium
Yeah,
carbonate they used.
correct. So and then use what they use.
I don't read. I cannot.
But yes, we need maybe some kind of reducing agent.
Salts. Yeah. I mean, co-precipitation is nothing but resolution, right?
Yeah, reduction, right?
Fraction.
No text can be extracted from this file. Sorry.
How come he's not reading in
Maybe
Chinese?
this Heaven or Cheng Wang can read later.
Yeah, it's all images.
Yeah, maybe can you just pass it into the WhatsApp chat so I can see, or maybe
I sent the link in our.
I'm putting it
oh,
here.
I didn't see it.
I sent it on. Okay.
Later.
Oh, sure.
So some thinking needs to happen. Uh, I feel like if we need the decision rests on whether we can make K2T. If you make K2T, I agree with Jayanta. Like the second part should be easy. This course precipitation route might be trickier because you'll involve a lot of metathesis, and then there'll be other side reactions. We don't know if it's thermodynamically favorable and stuff like this.
Uh, Co-precipitation is aqueous medium.
So Mahesh, can you look into this? Look
Yeah.
at
It's available in the market, K2T.
no.
Yeah.
So
I saw some pictures from
it's
in the stock.
but it's probably this hydrous salt.
No, no, it's saying K2TE.
Can you share your can you
Yeah, let me share the screen.
Hmm.
Can you see my screen?
Yeah, it's coming.
Oh, I had like similar experience
Potassium
previously. I
telluride,
tried to buy something and it's AI generated. This website.
but they have cache number. You can check with the cache number, CS number,
Let me
whether
see.
it's a true or not.
Dreams.
I'm pretty sure it's AI generated because
Man,
it
it's a
looks exactly
dreams.
the same as the previous
Okay,
one.
121420. Okay, let's check with the CS number because it's showing they use for batteries actually.
No, but I mean, if it's,
Okay, there are C.
I mean,
There is companies are there.
if you can get this,
Yeah.
yeah, see, it says reaction with air, it oxidizes. Maybe it's there.
Yeah, there is some. Yeah, it's there. This application, there's a website from US.
I would say it's a bit difficult. So even if we make it, we still need to like use an air sealed thing to do the XID, right?
No, but I mean, that's,
Nobody needs to use.
Use the glove box.
But how do
I
you
mean,
do?
if we go start use the glove box, then why not just make the three metals? Potassium, tellurium, and tin. Just
No,
do
no, but
everything in glove box.
there are a lot of steps, right? You
Why
got,
there are a
But
lot of steps?
I think you got to make sure that the reactivity is not there. Then you need to actually not do. Oh, are you saying carbothermal?
I mean, you can use DJS in glove box. You can also use carbothermal in glove box.
So
I mean,
instead of doing the regular quartz ampule heating, you're saying we just do carbothermal, then see
yeah,
if P forms,
yeah,
right?
we can just ball mill the powders, do both carbothermal and DJS. We have been doing it a lot of times in glove box. Just make the three elemental precursors and see what's going on. We have never
No,
do that.
potassium is more dangerous than potassium telluride, right?
I mean, of course, but in glove box it's still safe, right?
glove box is still safe. It's no oxygen there. So
1 ppm, is it dangerous? I'm not
no, I
very
don't
sure.
think so.
I don't know.
No, glove
Don't
box.
think so. Potassium should be okay
I think
in the glove
potassium is all
box.
right. Yeah.
But
Glove box.
the question is how do you, okay, so if it reacts and when you take it out, if it burns, then you have unreacted potassium. It's oxidizing, but it's a very small amount, so just be very careful. If it
Yes.
doesn't react and it's stable, then you have formed the actual compound. If it still is not stable, then maybe you have K2TE, which is unreacted tin and tellurium.
I got what you mean. So you want to avoid the unreacted potassium in the sample, right?
Hmm.
I mean, I don't think it's going to happen so much. I got a reason in the back. So I think potassium should have a good reason to react with tellurium because there is no just one compound in the phase diagram, if I recall. So there are other compounds that react with them. So even if it does react with like it doesn't form the target phase issue from like other other competing phases, maybe tellurides.
Okay, I mean, so maybe this is might not be a bad idea. We can just actually try to get potassium telluride, or you can start with the metal while we wait for the potassium telluride. Because the one advantage,
Yes.
if you start with the potassium, so the idea here is just to converge, right? We do carbothermal, okay, which is basically the same as a furnace, which I think Jayant has experienced, Hyvan has experienced. And we put metallic potassium, tin, and tellurium in the stoichiometric ratios and see what happens first, right? And take videos and pictures so we know what's going on. And be very, very careful when you take it out. Literally put a fire safety shield, gloves. Don't take any chances. Okay. The last thing we want is anything, even though it's only 1 gram. We've all handled potassium. You must have handled potassium when you were a kid, right? You can literally take a block with tweezers and hold it in air and it'll combust. It doesn't do anything. It's not going to explode, right? Hydrogen will explode, but potassium is not going to explode. It's just going to burn. So it's the same as any flame, right? So we try that, and then in the meanwhile, let's just get this K2TE. They'll probably send it in a nice sealed box. Then now at least the K2TE is a less chance of oxidizing, perhaps. Then we can check this all this stuff, right? Is K2TE uh, K2TE have less oxidizing potential than K metal precursor order, right? I mean, just putting everything in the chat so we can. Yeah, let's get the pure K because I think you guys are close. We spend this time. If we focus our effort and just make one of them happen, you'll be the first ones to sort of synthesize. That itself is a nice paper, actually. It's equivalent to Jayanta's paper on copper titanium telluride because he synthesized pure phase for the first time. And remember, for auto kappa, you don't need fully pure phase. 90% good enough. Okay, especially and there's a very low thermal. If I remember the data, the thermal conductivity is very low, like 0.5. Okay, so let's just focus our efforts on this and work on it. I think it's quite a fun one to try out. But again, we don't have potassium, right? Or we don't have K2T. Let's order both of them first. Christina, are you able to place the order?
I don't have the access.
Okay. Who's been placing the orders for you so far? Cheng Wang or Delvin?
Yep.
You just ask Cheng Wang to do it. He's not here today. Yeah. Just ask Chengong to help. Yeah. Any other thoughts, guys? I think this is very interesting. I will also try to join if I can, this week. I have things this afternoon. I need to do this appraisal stuff, but tomorrow afternoon I'll be in NTU. So I can also come by and take a look. And then I can also be there on Thursday and Friday, if possible. Yeah. Great. Good discussion. This is really fun. K is a very strong reducing agent. The potassium is already, like, it's obvious, right? Potassium is already oxidized for tellurium. And so the redox potential is lower for potassium telluride. So it's like a reduced salt. Okay, so I'm going to share this.
One question, if you make potassium telluride, is it stable in air?
No,
No.
No, then how are we going to take XRDMs?
I think
No.
it's, yeah, go ahead.
So I have the method. So I previously bought a small type of holder. You can use a Captain tape to do that. So unless it's very reactive, so for like about 20 minutes, it's doable. I have it in my office. We can do it straight away.
Okay.
I'll show you how this can be done.
Okay, so let's focus our efforts. I just hope we get the precursor soon, because if we don't get the metal precursor soon.
Yeah. Even there's some kind of oils or something you can anhydrous oils or solvents where you can use this powder and then do XRD in the holder.
Okay.
Anhydrous solvents. Yeah. THF.
All right, that's, I think, good discussion. We have a plan, right? Let's try to do carbothermal. I think that saves all this ampule business, and do it in the glove box. And then I don't think we need to do DJS in the glove box. We just like prepare everything. And if the KPE works, then we know what to do, right? Then you just fill it with argon. Then you literally have the K2TE working. You take that, put it inside, and keep it inside the argon. Even you can have a continuous flow argon into it, right? So you have a little valve. You just fill it the whole thing argon. Just place it there, and argon is heavier than air, so just displace it. There's no air or water vapor inside. So there's no air, there's no oxygen available for it to oxidize further. And then you can just load everything, hopefully inside the plex. It takes a little bit of doing, but I think it should be doable. Synthesis is not easy. Materials we've been doing are very easy so far. Huh?
I mean, especially these are the ionic kind of compound. Extreme ends of negativity. Electronegativity is high.
That's true. And potassium and tin are especially difficult. Tin likes to oxidize very fast.
Mm-hmm.
This is the other problem, right? Okay. Anything else anybody wants to discuss? Jayanta, I replied already, Partha. Okay, I looked through the paper.
Okay.
So I think you sent me the next draft, right? I need to look through it.
Yes.
I will look through it whenever I can. Same Pawan, I got the germanium, the GST sample.
GT, yes, yeah.
The GST. I'll look through it as well soon. Ivan, you want to update on how your trip was?
So I actually have a very nice slide. Not very nice slide, a very nice photo. So can I just share my screen now? Are you guys seeing something on the screen?
Yeah, it's coming.
I think it's on the wrong place. Sorry. Let me just resend the photo. So there was one guy that really impressed me. So he's from Lanzhou. So sorry, I need to send it in on my WhatsApp again.
Still, we can see your who chart or something.
Yeah, so I know. Still, you are seeing my WeChat. I'll need to.
While you load
So
it, Havan, you think, thanks for joining. I think I checked with the department. They will let me know. They said by the end of October. Okay.
Yeah, thanks.
All right.
So I haven't yet make a good slides, but so the conference I'm joining is called something like, I don't know how to translate it. There's no clear translation in English, unfortunately. So what they do is they deal with like those metals are non-ferrous metals and those rare earth metals. They use these metals to produce like structure materials, to produce functional materials, including magnetic ones. They also use this to produce like special alloys in the military uses. And this is a secret one. So it says that AI empowers 2050 structure alloy design. So how do you actually solve the problem from research, production, and then no from research, product, scale up, and then finally production. And what this guy really says is that you don't really need to produce a sample in the lab, and you don't really need to have a pilot scale production. What this guy actually did is that they built up a model. They learned the things. I think they get some of the data from lab and they get some of the data from the factory and they directly produce. So this unit is 3 ton. It's 3 ton. The file is 300 millimeter. They produce this the product directly without the small sample in the factory. Of course, after like a few times of fail, so this is the first time fail, the green one, 2025, 01110, the first time something blocked. So you got to work with the most experienced engineers in the factories. So engineers are extremely important in this process. They help you to avoid the problems. And the second time they have another failed. So the whole sample, it was on the edge of the furnace, not at the center of the furnace. So it's something definitely missing in whatever machine learning or AI models. So we need to have best engineers, of course. But once they fixed up all these type of common issues in engineering, they directly made the successful alloy steels corresponding to their predictions. But that's what they claim. And of course, they are not going to publish papers. It's something they're going to use for military, almost confirmed. So this is quite interesting.
Very nice. So where do they get the data to train the model from?
I mean, we also had a chat with Liu Yi, and China has the Material Genome project that's different from the United States one. The United States one, they think a lot about the theoretical data, etc. But the Chinese ones, they focus a lot on alloys. Half side, I think you know this two person is led by academician Xie Jianxin. He is an alloy expert, and the other side is led by Zhang Tongyi in Shanghai. So these two guys, they have built like two separate experimental database for them. They are not going to release this to anybody. I'm pretty confirmed.
Okay.
That's their fortune. And they somehow I think they use these fortunes to push this forward.
Amazing. Tons.
This is like, yeah. I mean, they're like what Danny is saying. So Danny was trying to like make an inorganic database and experiment, maybe using DJs, maybe using a cobblestone of whatever, but they already have the database of certain type. And
For certain alloys only, though, not for all.
yeah, for certain alloys on it for sure.
Okay. Yeah.
And for what I have learned is that they are all making different sorts of alloys, and they don't have the phasing problem what we are meeting. So for inorganics, our critical problem is we still probably need to achieve the predicted phase because all our property prediction is still linked to structure.
Yeah.
But for them, it's something they care nothing about. What they care about is the microstructure.
Yeah, I mean the alloys are also, yeah, the microstructure is usually by multiphasic and
Yes,
much harder problem actually, to be honest. So I think this is they show something very beautiful, but it's not so easy.
it's not so easy, clearly.
What they're showing is just more luck than anything related to AI. This is my
I
opinion.
don't know.
With
These
alloys,
guys are crazy.
yeah, with alloys it's very hard to predict like things like, I mean, you can get mechanical properties and which is under The linear regime, that's okay. But if you want to go to fracture or failure, it's impossible.
Oh, that's crazy.
It's impossible. Linear properties is still doable. Like elastic properties. Elastic properties are doable.
Yeah. So and another thing is about the LLMs. I have been doing on ICSD. So we went to Xiaonan's lab, and so they have like a lot of industrial projects. So what they basically do is they just secretly downloaded the papers and the companies, they paid them some money, like about say 100K Singapore dollars or 200K Singapore dollars in this range for them to extract some data from the papers. So what I would say is what we have now is slightly better than what they are doing, but I'm not sure whether we are having the market in Singapore here. So I'm not. I think Kira, you still recall this paper? We did this about 2 years ago, right?
Absolutely.
Uh, Tway, right? So at that time, the accuracy wasn't very high. So I did this chart together with Andy and Tway. So I defined what's the gray area, what's the accurate area, and what's the yellow area. So the blue area is something as an experimentalist I confirm is 100% correct. And the gray area is something it is correct, and but the paper did not apparently use word to say it, but the LLM still captures it. You got what I mean, right? So not every paper put up all the details, but the LLM has the power to imagine somehow and still correctly capture it. The yellow part is the serious error rate. So at that time, you can see the error rate is still in some range of like 10, 20 percent. It's still pretty huge. So I have all the ICSD, 75 of the corresponding ICSD papers on the local workstation. I was able to verify 75% of the full ICSD. So there are three models I have been trying. The first is a single large model with the Gemini 2.5 Pro. So it is able to give you like say 85% of accuracy against me. So I verified manually 100 papers from 0 to 100, and the accuracy rate of Gemini 2.5 Pro is about 85% or 95%. So on different tasks, you just have a feeling. The cost is about $0.1 to $0.3 per paper. It's very unsteady because the reasoning process is sometimes you don't know how much money it's going to cost. So the second version I upgraded is I use multiple chip models. It's including Gemini 2.0 Flash and 2.5 Flash Lite. So it has a 90% of accuracy on versus the 85. So on the first task, and the second is 95 to 97, and the cost is much lower. It's 0.01 against 0.1203. So this is much better. So above that, so if these two models they doesn't agree, I introduce another slightly more expensive models, the 2.5 Pro and 2.5 Flash, and this largely increase the accuracy from 90% to 96%, and temperature and pressure extraction rate is 99%, and the average cost for all the ISSD per paper is 0.05 cents. So about the performance, we're definitely far beyond what we are able to achieve like two years ago. Now, if we extract something, we're pretty confident. And from the ICSD, what you can see is that the temperature and pressure recorded in ICSD across different like characterization method, including single crystal excited, powder excited, neutron diffraction, electron diffraction, and others, they are almost all approaching like 90% expect for these others. So like 90 plus percent. It looks good in ICSD, but if you look at those of materials that's characterized in non-ambient conditions, say in non-ambient temperatures, there are 43% of error rate, and those being characterized in non-ambient pressure, there are like a 35.5% of error rate. So it makes a lot of sense because ICSD data, when it comes to non-ambient, if it doesn't know, then you will tag it as 298 K and 0.1 megapascal. So it's understandable. And now I would say that we have a very robust workflow to do relatively large scale structured data extraction as of now.
So can you run this tool for the K2SNT5? What do you get?
Um, I
Basically,
mean,
what I did right now was a single large model, right?
No. So
Prompted it.
this is a structured data extraction. It's kind of like the lemmat. You
Mm.
go what I mean? It's not a predictor.
Mhm.
So but actually what I've done in Cursor is that I try to ask it to identify all the possible reference that may be related. So what I do in Cursor is first, because our target phase is K, S, and T, right? So if we want to dig in the synthesis, we want to understand what are the what are the related phase diagrams. They are NA, S, and TE. They are NA, S, and S, these sort of things. So I ask it for it to search relevant information in Cursor
Right.
and produce like 5 to 10 markdown files as the background files. So they are like different phase space. And once they understand the synthesis in different phase space and ask it, try to predict this K5S and TE. And what comes out is that it let me just use the elemental precursor.
Yeah, maybe. Is that what it said? You tried it?
I mean, yes, it's in my
Okay.
project. I mean, not even writing paper, I'm using Cursor. It's much better, man. What I really need to do is I create a folder. I threw out about 80 PDFs inside, and it understand what's the style, what's the background information, and it will just write it for you.
Perfect. Okay, so even that method for K2 SNT5, you should write this up, by the way. This is a nice paper to write, like for AI format or something. Just write it up very
Man, this is a nice work, but we are going to get sued by the publisher.
really. But you're not releasing, you're just releasing statistics, right? You're not releasing the data.
And I know because I downloaded like about 150K
Hmm.
PDFs from Science Hub.
I see, I see.
You got what I mean, right?
Unless we have a license, you cannot publish this. Maybe that's what you mean.
This is like pretty dirty.
Got it, got it. Okay. Okay, so thanks for sharing. I think this is very useful. We can use this without publishing it. But at the end of the day, yeah, I think we should let's focus on you guys have some very unique expertise, okay, like with carbothermal and thinking about all this in a different way. So Jayanta, Haiwan, I think Delvin is not around, but work with Christine. Let's order the chemicals. And I would suggest just spending like a week trying to get it done, right? I think it'll be amazing if we get the precursors in a week or 2 weeks and we spend a week and we get something good because we actually made then a new compound through a new synthesis technique or an old compound through a new synthesis technique. And if we can pelletize it, then we can measure thermal conductivity. That's pretty amazing. Okay, I don't think anybody's done that. So yeah, I think it'll be good to sort of focus on this because I think all of you have other things going on, but when you put things collectively together and let's say Christine is taking charge of synthesizing this material, I think it's possible to do it. Okay, so please spend time on this. Okay, great discussion. This is really fun.
I have couple of slides, so like
Go ahead.
okay. So like I think I could not remember I show this one. Like this is like after 2% titanium addition.
Mm-hmm.
So like it's stabilized throughout like 350 to like around 600 degree. The phase is stable.
Mm-hmm.
And recently like this paper is came out I think like 5 days ago. So in this paper actually they showed so they actually using like 315 composition, but they don't get the phase pair compound. So that's why
Got it.
they actually varied the copper and telluride composition, but for the like polycrystalline sample, but they actually minimize the uh, secondary phase like LAT2, but still like for polycrystalline sample they don't get phase pair, but for single crystal they grow from another method. So they in that method actually they got the phase pair compound. So actually it's like a little bit justified with my like 2% extra titanium addition. So because like it's like from copper 1 it's like copper 1.5, so it's like huge. So that's I think justified with my result, but still actually the extra 2% titanium suppress the copper telluride. But like how it suppress the copper telluride, so this still like I don't know like how. So I'm thinking like so it's like trial and error, right? So I add 1%, it little bit suppress 2%, but so is it like changing the like this one like the formation energy or something? I don't know. So like I
So
want you, yeah,
I think Jayanta, you can talk
yeah,
to Savia about this.
okay,
What they do is they look at the stability of competing phases in the presence of high or low chemical potential of each element. So,
okay,
it basically says, I mean, I can translate that as saying, in the presence of extra titanium, because the chemical potential of titanium is high, then the copper telluride is not likely to be formed. They usually look at vacancies, but maybe they have some ideas in looking at, what is the possibility of copper telluride stabilizing in the presence of excess titanium. And when you use those arguments, even with like free energy or just even simple
good.
formation energy, that should guide you to say, yeah, actually it makes sense.
Yes, even like every like few papers I saw like they just added and suppress it, but how it's work actually, so what is the
Mm,
main reason behind it, so this is not still clear actually. Yeah,
mm.
Jenta, so another
yeah,
thing I think you can do very easily in like about 5 minutes is you're now already on materials project, and another button is the purpose diagram, so which tells you to different like concentration of like elements, what are the like the chemical potential, and if you increase the titanium and what's going to happen. So maybe tomorrow when I'm on campus, we can just have a look at it together.
okay, yeah,
Yeah.
fine,
And same
So it's something
what
easy.
I'm saying. Yeah.
okay. And like so my assumption is like it's like near copper telluride binary line, so that's why like for without titanium like there is maybe in ball milling some titanium is deficient or something happening, so that's why the copper telluride is stable and excess titanium can react with that copper telluride actually.
How did they explain this in the inorganic, the lanthanum copper?
No, so they just told like so they varies like trial and error, they varies the copper and telluride,
I
then
see.
they got like less like LAT to phase, so they don't explain how actually it's like suppress this binary phase formation.
All right.
And actually another reason like its stability is very narrow actually, so from synchrotron, so from DSC actually, so the like cubic phase is decomposed at like 463 Kelvin, and even from synchrotron also like it show like it's partially decomposed to copper telluride and titanium telluride above 460 K. So like it's quite challenging to stabilize that phase. So if you like uh, slow heating or slow cooling, so above 460 K, then the phase is decomposed. So it's like quite challenging to stabilize that phase.
Interesting.
So even like SPS or another any weight, so you cannot stabilize that phase.
I mean, this is we've been thinking. So both Chengwang, Pepe, and all that, but Mahesh is here. We've been thinking about this, rapid cooling. What happens, And so what happens if you think about it, right? You're heating up very fast. So putting some heat, joule heat, whatever heat, right? You're putting
Yeah,
heat very, very fast.
fast.
And your dwell time is how long are you heating up the material? Is there a chance for the phase to form or not? So what we found is that with DJS, if you look at the time temperature profile, right, for AGSBT2, it's not just like going up like this. Like, the time temperature
Yeah,
profile is not like going up like this and cooling down like this. Instead, what's happening, right? It goes like this near the melting temperature of something. I think silver telluride. There's a neck. It goes up like this. So what's happening somehow is that it seems like in these ionic compounds, there is some ion diffusion assisted migration and stuff, which allows the heat to be transferred very efficiently to the rest of the precursors. So in this time, when there's a small dwell time and then we have some cooling like this is what a DGF profile looks like. Okay, what ends up happening is that you actually have a good chance of forming the pure phase here because your heat is going into really producing the phase. And the cooling doesn't matter so much, even though the cooling is a little bit slower than, let's say, ultra high vacuum, the UHS technique. But this is actually good enough to form the pure phase. So for things like this, where there's a narrow stability window, there is no time for this because anyway you're cooling very fast, right? There's no time for it to decompose, but the energy budget is efficiently used to create the primary phase. I think that's sort of the idea.
Yeah. But Jayantak is little different. Ours is even at temperature is like there's no secondary phase. Here, if you go to the high temperature and cool down, there's a secondary phase forming, right?
Yes. So I was like,
Yeah, but I mean, that,
This one quenching can help.
yes.
mm, no,
Yeah.
in like they tried quenching, but it's not working actually.
Okay.
Did you try quenching with DJS?
No,
DJ's
no,
quenching.
no. After DJs, so it works, right? But it needs extra titanium addition, then it will work.
Yeah, I mean that's my point, Mahesh. Like with extra titanium in this narrow
Mm,
stability window, in
Mm.
bright chemical potential, he's forming pure phase.
Yeah.
mm.
No precipitation. Even after you cool down, there's no precipitation forming.
Yes.
Okay. Below that
Fine.
certain temperature, right? If you stop the reaction below certain temperature, 480.
No, like after 2% titanium addition. So if I like
Yeah.
synthesizing using DJs, so it's like as
Okay.
the cooling is very fast. Even if you saw this paper actually, so they actually forming the lithium copper 3 titanium telluride, but when they cool down, like for
Mm,
like below the 400-degree, the phases started to decompose.
right.
This copper telluride is forming, so you cannot avoid using like any like
Mm.
slow cooling or something any other way.
Mm.
Okay.
What is the temperature of synthesis for this material?
This is 600-degree
600 Celsius.
uh, Celsius. Yes,
Do you have the time temperature profile?
I have at okay, just give me 1 minute.
Also unrelated, I forgot like this material you're not able to get you wanted to do SPS, right?
Yes, but I think like hot press also can work. So this
Okay.
is looks like.
Hmm. So you see around 700 K, there's a change in so it goes up very fast to 700, right?
Yes, like this is cannot record the temperature, right? So it
Mm.
can record after 300-degree the IR
Okay.
sensor.
I see.
Is the initial is ball milling? What is the is it stoichiometric elements or something already is any compound form? Did you check
Uh,
the uh,
okay. So this is
Mm.
actually with 2% titanium addition. I did the
yeah.
radial definement and the phase fraction. So initially after ball milling, there is like copper telluride, copper 1.4 telluride, telluride, copper telluride is there.
Amazing.
Then after like 300, so we can record only 300
Okay.
to above. So 300 the phase is like 2.4%. Majorly it's like copper telluride. Then like after 350 with addition of 2% titanium, it's like this is for 2% titanium addition.
Nice.
So the phase is started forming still
Amazing.
here. Then after that it will little bit decompose.
Yeah.
Okay, great. Yeah, so with some theoretical explanation should be sufficient. You don't need to
Yeah.
wait for some fantastic theory. Okay, just
Okay.
some
Yeah.
theoretical support to show that should be
Yes.
good enough.
Yes. And actually, Andy calculate the like local telluride coordination of
Okay.
like how much bonded with the copper. So it's
Okay.
like at increasing temperature, the telluride bonded with like 4 copper is decreased and increasing like with 3 copper and 5 and 6 copper. I'll just little bit explain about the coordination environment. Like titanium, like this is for the like cubic one, because
Mhm.
for rhomboidal one is little bit more complicated. For cubic one, the titanium has like 4 nearby 4 telluride, so it's like tetrahedron, and the ordered copper site, so which is like 3 C sites, So it's also from tetrahedron, and the disordered copper side, it's from the like distorted octahedron of and but like their 3 bonds is short and 3 bonds is long. And the titanium coordination, like this is varies, sorry, tellurium coordination varies from 4 to 7, because like tellurium has 1 bonded with titanium and 3 with the ordered copper. And like according to the availability of like disordered copper, so it varies from 4 to 6. Like so there is another 3 actually. So like I think this can be like help in the local coordination, and as well as like how the thermal conductivity trend is there, because like if the telluride coordinate with more copper, then there is less availability of the lone pair of telluride is there. So like which can like uh, the local distortion might be less actually. So
I mean, this looks fairly complicated.
This is
yeah,
slightly correlating with the Kanishka's one presentation, like coordination changing and deficient means it's kind of meta. He told,
Maybe.
yeah, it's not a covalent, not ionic, it's metavalent compound, something he told, right? It's like
yes, yes,
deficiency of the number is nothing but
yes,
those.
yes. Yeah, because like these three are like kind of interaction, like this disorder copper is kind of interaction with the telluride, because telluride has the lone pair and it can like coordinate.
Where is the three coordinate? Like tellurium three copper. Where what is the structure? Tetrahedra I know 4 Cu, octahedra
Yes,
8
yes.
typically. Where is the third three structure?
Third structure, sorry,
C 3 Cu.
uh, you are talking about this one.
Yeah, yeah, 3C. Yeah,
Oh, this 3C means this,
coordination.
yeah, this one ordered copper, this one like 3C is the ordered copper, and the 4D side is actually the disordered copper one.
I think it's the
So
Wyckoff side.
yeah, the Y side.
Always say it.
The copper in the 3C Wyckoff side is
Mm-hmm.
still tetrahedral bonded. Is that what you're saying? Right?
Yes, yes, it's tetrahedral bonded with that telluride.
How does he do this figure D? You're
Yeah.
doing repeated bonding at different temperatures?
Yes, actually the different like there is like zip file at different temperature. So he actually ordered the structure actually. So he take the supercell and he calculate like how much telluride is coordinate, like nearby there is how much bond with copper.
So all this is already in the paper?
No,
Hmm. Okay.
even actually we like solve with like PPJ group at 310 Kelvin, at 310 Kelvin. So there is weak
Hmm.
reflection spot also there. So which indicate this is the rhomboidal phase at 310 Kelvin also.
Yeah, that's the new phase.
Yeah, like new structure actually. Okay. And actually I do the like transport property, but like if I cut like other sample, the cycle is like the data is repeatable, but there is some issue with the cycle. So I run 4 cycle, it's like little bit degrade. So Mahesh told it's maybe due to I cut the sample with the oil or something else. So he suggests me cut the sample without oil or something.
Hmm.
I mean, other samples, silver telluride or bismuth telluride, no issue. Whether you cut with water or this one, somehow this sample absorbs this because he gave me sample when I try to make this connections with soldering rod. When I place some solvent still coming out. It's kind of
Odd.
more bond lengths or something like more voids in between the layers where this oil is going. Hello, yeah,
Yeah,
this.
so I'll just try to like I just try the pristine one. So if it gives the same value, then I think like
Mhm.
actually like there is even in solvonate compound, so there is not fully stable. Even people are doing solvonate compound by hot pressing, so they don't do SPS. So they just do hot pressing and just even they
Hmm.
don't mention the density also, because the density maybe is very bad, not even like 98% or something.
So at the end of the day, you want to show low thermal conductivity, right?
Yes.
Yeah, you might have to do SPS. But if the density is not good, then that's a problem.
Yes, like if I do like at 150-degree SPS, and like I try, but I know it's the density is not like 98% or something.
I see.
Even
Okay.
in, yeah,
You don't have power factor here.
uh actually I did not incorporate the power factor, but I have the data. Just give me 1 minute.
But it's small, right? You see,
I
Yes,
think
yes,
need
yes,
to,
yeah, power factor is very small.
conductivity is pretty small, 20.
Because I
I think
suspect
still
the
need.
conductivity. I suspect the conductivity is deteriorating by cutting. So just one time without any oil and something. See
Exactly.
the
Yeah.
Just give me 1 minute.
Are you cleaning it properly?
Uh,
I mean, one of the biggest issues is going to be, I mean, if you do both electrical and thermal, right, on the
yeah,
same side,
One
in the same
six.
direction, even if the density is not the same, you can make some sort of argument that in your cross-sectional area is the same porous area is coming. But it's not great, because if you look at a ZT, you have to
mm,
report ZT. You cannot report individual transport.
yeah, like VT is very, I think
ZT will be very low.
very low, like 0.08. But like I cannot measure beyond like 200-degree, right? So like it's cannot go up. This is not for thermoelectrics.
Conductivity is pretty poor. Where is the conductivity values?
Yes.
Ah,
It's not
but
bad.
you already removed the copper, right? So you're still losing the mobility is a bit weird.
um
You have the hall, no hall, right?
yes
Yes,
there
I
is.
have hall. The
Base.
key demonstration.
Uh,
Why is the densification not working with SPS?
He didn't go to high temperature. What I suggest, deval is only 10 minutes, right? Chanta?
Yes. No, actually, last time I increased 30 minutes or something.
Okay.
30
Improve?
minutes. No, not like not 98%. So it go like 92, 93, like not
No,
90.
compared to last time.
Yes,
Compared to
yes,
last
yes,
time.
yes, yes. Compared to
Okay.
last time, it increased. Even I increased the pressure also. So it's
How
like
much?
64 megapascal or something.
Increase to 10. Okay.
And you don't
you
want to go
don't
to
have.
high temperatures because you think it's going to phase separate.
No,
Yeah.
because the phase is partially decomposed,
Yes, so how
Uh,
much decomposition do you have?
like 10%.
I think there might be an argument to be made where you get a fully dense sample with low phase fraction of the phase impurity, but the bulk phase is preserved. Then we can do this TDTR, right? We can give it to econ and then they look at the large grains and extract the thermal conductivity and show it's low.
Mm.
Same as what we did
Okay,
for the DGS Mahesh.
Yeah. Yeah. You
okay,
can do little high temperature and high same. Got it.
okay.
But don't cut with the water because the it's deteriorating the electrical conductivity deteriorate because of what kind of solvent there. And thermal conductivity usually might be high, um, it might be low. Right now you're getting because of presence of solvent as well.
Okay.
I discussed with him. Yeah.
Yeah, but so try to find the sweet spot for the SPS.
Yeah.
Density is like 95% and above, and
Mm.
you don't have too many precipitates. That's the
Yeah.
trick.
So like if I go high temperature, then like when it's cool down, then again it's forming the phase. If
Yes.
the cool down is very slow, then like, it will there is more
Forms
more more binary phases.
Okay. Yeah.
Even
Sure.
even 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 this is also the synchrotron data. So like you can see in the cooling cycle, so there is like impurity.
Yeah, I got it. We'll play with SPS two three things. Yeah.
Yeah. And it's kind of interesting. Like we've managed to make the pure phase, but the density limitation doesn't allow us to measure transport.
I
Yes.
asked another question to him. Is that bond length typically higher compared to our AST and BI material? Yes, it is. Like it's kind of the bond length is 3 point. right?
Yes, it's 3.2.
Yeah, like it's kind of there's some gaps. So this longer bond length or something. So these water molecules or oil is going inside. So it's giving you, because of less density, is another oils are going in. It's deteriorating the electrical transport.
Mm.
I mean, really nice
Okay.
work. We try a little bit more. Let's get some,
Okay.
and then we'll see what we have to say about the thermoconductor.
Yeah.
Okay.
Okay, that could work. All right, thanks, guys. Nice meeting. Lots of good discussion. Lots of things to think about. Like even for the Kappa Gen project, I feel maybe we should just simplify, right? Like we did not put this criteria that if the precursor is not easily available, don't do it. If the precursor is oxidized, don't do it. You know, it's like we need to add these criteria to the filters somehow. And like we start with a very tight subset because generative models, like stuff that we're very, very familiar with, like work with germanium, tellurium, selenium, like tin, silver, stuff we're very familiar. And then only between that, if we find something interesting, then we go. Anyway, lots to think about. Okay,
So
thanks.
actually, just before the meeting end, I think there is one thing we can do very easily. I haven't been yet trying now. So what I can do is I try to download like every synthesis papers in our group and in groups that we are able to get access to the lab, and then we form a folder of say about 200 PDF papers, and then I just let cursor say if there is a new candidate, just search through all the papers and see if you think these people that are able to make it and how they will be able to make it. It's pretty straightforward. I mean, the method where GPT suggests is different from what we are able to do.
Yeah. Like the carbotherm idea only comes to us because we wrote the papers. That's what you're saying.
Yes,
Otherwise,
yes,
we have to do the quad ampule and
yes.
absolutely.
Yeah, I'll try to make this because it's easy and quick.
Great. Great. Lots to learn. I mean, I think we're moving very fast with this project. Okay, so I think, Christine, I know you and Delvin did an amazing job preparing the catalyst samples. Thank you. I hope we get a little bit of a break, but let's go one compound focused to try to make it and get everybody's help. Don't be afraid to bug anybody. Okay. You need my help
Uh,
on something, let me know.
yeah. One thing is, do you think if it's possible to like buy a small PC for like the to implement the LLM process in the lab? So there are like a few things. So the first is previously I've already showed their Wing Chun Guang, and so because we have a lot of safety checks, it takes us a lot of time. So now I already have wrote an app which able to you just take a photo of the bottle and it is able to recognize and inject into the database. So we use this, and already in CARES Lab, we have already like spent like about 2 hours to screen all the chemicals in CARES Lab is successful. The accuracy rate is very high, and so in the future is able to like reduce our time. Say previously we need about half day to do the process, and now we just need half day, a few person to do the process, and now we just need 2 person, one take picture, another pass chemicals, and the whole time for one lab, our lab can be reduced to say maybe 1 hour. Also, so this is one of the application, and the second one is the synthesis generation. So because cursor is still like a personal account, so either we can just have a like a group GPT account, we can just link it to Codex over there, or I can just implement the Qwen, which is a free model. Over there, I can set up all the markdown files, the agent files over there, so people can use it directly.
Yes, I mean, I think Danny has a cursor account that we paid through Bears. So I think just ask Cynthia and
Yeah.
she'll have a chat with me. Like we'll try to find funds for a terminal or laptop that we can put in the lab that you can run things off of. Right. And
Yeah, it can be pretty cheap, like $500 or $700 is
I
pretty
actually
fine.
have an old laptop that was issued NTU MSc, which is actually
Oh,
pretty.
that's amazing.
Yeah, it's a Mac. It's not the latest Mac, but
I mean,
it's
it doesn't matter, man. It doesn't matter.
it also has GPUs on it. So like,
Oh, that's amazing.
yeah, just let you guys know, like for the Kappa Gen project, I actually ran my own code with not even just Copilot, which is really fun. I spent a lot of time doing it, but like a lot as in like maybe I spent about 3 to 4 hours properly. And if you don't prompt it properly, if you don't tell it what to do, it does a crappy job. It goes and like tries to debug random shit. Just no idea. So if you really give it the right knowledge, then it actually does the coding pretty efficiently, I think, and very
Yeah.
very clean. So point is that you can then just use that laptop. So I'll try to find that laptop. It's sitting around my house somewhere, and I'll just like erase everything there and give it to you, and then you can
Yeah.
just scratch, just use it, like just keep it in the
Yeah.
lab.
Yeah, then I would just try to make a few apps and then people can use a few apps on top and people can use it without too much concern.
That'll be very nice. Okay. Thank you guys. See you
See you
soon.
later.
Okay, see you later. There are chocolates, so come in person, okay? See you.
Unfortunately, I can get it.
Uh,
Bye.
okay, never mind. We'll keep one for you. See you,
All
Christine.
right. Thank you. See you.